So we're now going to be looking at our learning intention 2.6, which is I can use exponential functions to model different scenarios. So we can use exponential functions for lots of different applications, such as modeling bacterial growth and decay, population growth and decay, as well as compound interest. So those are the few, I guess, main ones that you will mostly see use exponential functions to model their growth or decay. So, for instance, for our exponential growth and decay graphs or equations, they're usually described by the following function here. So we've got a is equal to my a naught b to the power of t. So in this equation here, my a naught is what we have as our initial quantity, and our b is a positive constant, and our b to the power of t is also known as the growth factor. So the a in this case, I always like to think of it as like an amount, right? So we're changing an amount, the amount's either decreasing or increasing over a certain amount of time. And obviously that time can be whatever weeks, hours, days, whatever the model is specifying in this case. So for my A of 0, so my initial quantity, this could be 20, 100, 1,000, anything. So usually we'd think of this as, what is that y-intercept at? In terms of this B, however, so I said there's a bit of a growth factor. So for this B, if this is greater than 1, then this represents a growth. Whereas if my B is less than 1, then this is representing decay. So, for example, just so we can wrap our heads around this a little bit better, if we were modeling a population of bacteria, so we wanted to see what their growth or decay is. So in this case, it's saying that this population of bacteria is increasing at a rate of 30% per hour. So because it's an increase, then my B would have to be greater than 1 to represent growth. So it's saying that it's increasing by 30%. So of course, 30% as a decimal is 0.3. So that means we need to multiply my initial amount or initial quantity by 1.3 to have a 30% increase, as we can see here. So in the next line, it says that the original population, P0, is 20 bacteria. So that is my A to the 0, or in this case, it's using P, so P to the 0. And it's saying that the population is increasing after a certain amount of hours. So T in this case is now in hours. So for the first one, my initial P, so P at time of 0 hours, of course, I was beginning with 20. After 1 hour, I've increased by 1.3, so increased by 30% after an hour, so represents like this. After 2 hours, I've got 20 times by 1.3 to the power of 2 to represent that 2 hour. And then finally, my P of 3, so after 3 hours, is 20 times by 1.3 to the power of 3. Okay, so you can see that my exponent here is increasing at the same as however many hours have passed. So therefore, we can say that the exponent function that represents the growth of the bacterial population is P of n equal to 20 times 1.3 to the power of n. So n being however many hours it is that has passed. The other thing that we want to consider when we're talking about exponential growth or decay is this concept known as half-life. So you might have heard it before in chemistry. It's quite common talking about like isotopes and their half-life. And in this case here, we're talking about the decay. So half-lives are always talking about a decay in the amount of mass that originally was there previously. So of course, the term half-life is as it sounds. So our substance that we are measuring is decreasing by half each time. So we're going to have an example of both half-life and using our function or form up here to have a look at a few examples. So remember, make sure you try to pause this video and have a go at doing these yourself.
Our first example is an entomologist monitoring a plague of locusts, and he's modelled this using the following function, which is a to the n equal to 1000 times by 1.5 to the n hectares. So it's saying here that our n is the number of weeks, and we can see that in several places here. And we can say that our A here is the amount. So the first question asks, well, what is the original affected area? And just having a think about, well, if we've got our n is a number of weeks, we know that the initial affected area would be when my n is equal to 0 weeks. So pretty much just plugging when n is equal to 0 into my function. So I'm going to have a to the 0 is equal to 1000 times by